So on Friday, it should be like this. L1 over V, L2 over V. So if this is the case, then it should be, it's more simple, I think. T2, T1 is L2 minus L1 over V. Okay. Okay. So we have to correct this one. Sorry about that. You should ask. Yeah. I just realized it after the lecture. So yeah, I should tell you today. Okay. This is number 4, I think. Number 4. So it should be L2 minus L1 is equal to V delta T. Okay. So this one could be L1 squared V squared half 1/2 minus L1 V delta T. Okay, we also use this approximation. Okay. If this is the case, then it should be L1 times 1D squared over L1 squared. Okay, minus L1 V delta T. Okay. Then the solution is much more simpler, I think. If this is the case, so this we get that L1 1 plus D squared over 2L1 squared minus L1 V delta T. Okay, we get that this should be, sorry. Okay, it should be D squared over 2L1 equal to V delta T. So we get this L1 is D squared over 2V delta T. So this is the correct answer, this one. Sorry about yesterday, not yesterday, on Friday. Yeah. So we have D, okay, as stated in the problem, also V, okay, the speed of the sound, and delta T, right? Yeah. Then you will get this L1 and you will get L2 just using this formula. Okay. Is that clear? Okay. Hello? Any question? This is for number 4. On Friday, I made a mistake. Yeah. I just realized it after the lecture. Okay, any question? Hello, hello?
Not
No
yet, sir.
question, Pak.
Okay. Faza, please change your name. Write first your student ID.
Oh yes, sir. Will do, sir.
Faza, mana nih? Not yet ya. You have to change your student ID. Student ID and name. Okay. So we shall continue to the next section about interference. Okay. So the lecture yesterday will be replaced on Friday. Yeah? So for Friday, we do not have tutorial session, but only a lecture. Okay. So yesterday, because I have vaccination, so I have to take a rest after the vaccination. Okay, you can open your book, Holiday Resnick, about interference. Okay, this basically interference we have discussed it in the wave lecture. Yeah, the lecture about the wave, which is the interference is nothing but the superposition of two waves, two or more waves. Yeah, two or more waves. Okay. So in this case, we consider the light as a wave, okay? So it's the wave theory based on the Huygens theory about the waves, okay? This is, for example, this is the wave front here, okay? The wave front of the waves, okay? This is a propagation of plane wave in the vacuum. Okay. So as we know, the light, yeah, could also refracted, could be refracted. If, for example, this light coming from the air to the glass, okay, they somehow, well, maybe the right word is bend, yeah, bend when coming to the glass, okay. So somehow there is an angle here, okay. This angle theta here, sorry, not, this is the angle of, basically this theta, this theta here somehow is related to the angle of reflection. But refraction is related to the angle where, with respect to the normal axis, okay. And also, if the light is refracted, so it has to satisfy this equation, okay? This equation coming from if you solve the Maxwell equation on the material, okay? So it's really it's quite complicated to derive this simple relation, but at your level, we just only give the formula, not to derive it, okay? So lambda 1 over lambda 2 equal to V1 over V2, okay? This lambda 1 is the lambda in the air, for example. The medium where the light incident, okay? As the incident wave, okay? And then this lambda 2 is the wave in the glass, okay? So after the light coming inside this second medium, okay? And also the speed of the light also different, yeah, in the air and also in the glass. Okay. Okay, so basically, this relation also coming from the Maxwell equation in the medium. Okay, this 35(3). Okay, so this index of reflection is equal to C. C is the speed of light in the vacuum. Okay, while V is the speed of light in the medium. Okay. Okay, so okay, this is an alternative derivation of this formula, this 35(1). Okay, so if we consider, for example, this triangle here, this θ1, this is λ1. Okay, this sin θ1 is equal to λ1 over hc. Okay, hc is h is the Planck constant. I'm sorry, yeah. Sorry. Just a moment. H is this point. I'm sorry. This point. So this, if you see, I will make it. I will zoom it. Okay, for you. So this H here. Okay, HC. Okay, this is λ1 sin θ1. Okay, sorry. Okay. They use the same symbol. Yeah? They use the same symbol as this one. The C here is not the point. Okay, this is the C here is the speed of light in the vacuum. Okay, while C here, okay, this is the point. Okay, HC is this one. H is a point, C is a point. Okay, yeah. I mean, yeah. This book should use different symbol. Okay. So, and also this is for in the air and in the glass, the second medium, we have also similar like this. Okay, if we divided sin θ1 over sin θ2, then we will get this equation after applying this 35.3. Okay. So if this sin θ1 over sin θ2, by applying this the index of refraction, we will get this Snell law of refraction, this 35.6. Okay. Any question? Any question about this derivation? Anyone? Okay. Let's continue. So you see that because this V here, it's depend on the index of refraction N here. So it should be this lambda also depend on N, okay? And also this frequency. Okay? In general, okay? But if we see that this Vn is V over lambda n, while lambda n is lambda over n, and C And then this V here is C over N, then we get this Fn is nothing but C over lambda, okay? And this is equal to F, okay? So it means that the frequency, like in the frequency, it doesn't depend on the medium, okay? It doesn't depend on the medium. So this N here is the number of waves, like wavelength. This N1 is L over lambda N1, okay? So, and this is N2 here. So if we subtract it, this N2 minus N1, we will get that L over lambda is N2 minus N1. So this, the number of wavelength, the difference with the number of wavelength is proportional to the difference between this index of refraction. Okay. So we will discuss it later. Sorry, this is diffraction or? Okay. Okay. We will discuss about diffraction later, but we will consider first the interference, okay? The interference. So the interference means that this is the superposition of the waves, okay? And in general, for example, if this is the incident wave as a planar wave and goes into, for example, this single aperture, this single slit, okay? And then they have these two slits here, okay? These two slits here, S1 and S2. So we omit the width the width of these slits, okay? We only consider the distance between two slits for interference, okay? So we will get like this. This is maximum bright, dark, bright, dark. Okay, maximum it means bright. Okay, so in reality, this is the picture, yeah, in reality. Okay. So this is basically with the simplicity of the Young interference. So we have this planar wave as the incident waves, okay, and this is two slits where we omit the width of the slit, okay, we only consider the distance between the slits, which is d here, okay. As you see that if the just a moment. Okay, so this is the two slits here, this S1 and S2, and this is the screen, okay? And usually the screen we consider is far, far away from the slit, okay? So because the screen is far, far away, the wave that coming from S1 and S2 can be considered as parallel waves, okay? But they have different phase, okay? Because the distance of two slits, okay? This path length difference delta L will cause this interference phenomena, yeah, bright, dark, okay? So let's see. Maybe I stop here. Okay, we will. So basically, we have, this is S2, this is S1, okay? And this is R, this is R plus delta R, and this is, I think, theta, yeah. Okay, theta. This is theta. Okay. So C1 is, we have the same amplitudes, sinus K delta, R plus delta R minus omega T. Okay, and C2 is A sinus K R minus omega T. Okay. So the interference means that we have this C here as C1 over C2. Okay. So this is basically A sinus K R minus omega T plus B plus sinus. Okay. Any question? No. So using this formula, sin A plus sin B, I think this is sinus A plus B over 2 cos A minus B over 2. Okay? I think. Okay? So we will get that this C here equal to just a moment. Yeah, I think that's one. So this A here times cos V over 2 sinus okay. So basically the intensity is proportional to this C squared. Okay, it's basically A squared cos squared okay. If we average sorry, it should be this. This is the average. This one. It should be this one. It should be a half. Okay, squared cos squared v over 2. Okay. So destructive means that this is dark. Okay. Dark means that cos v over 2 0. Okay. So we have should be v over, oh sorry, this v here, I'm sorry. This v here is k times delta r. Okay, this should be k d sin theta. Okay. So basically this should be n plus half pi, right? Okay. For n equals 0, 1, 2, etc. Okay. So because this v here equal to this one, okay, I get that this k d sin theta minus 2n plus 1 pi. Okay. Sorry. Let just this become this one. N plus half pi. This is 2. Okay, because this is 2 pi over lambda. Okay. We get the sin theta n plus half pi. Okay. So we will get, okay, this d sin theta equal to n plus a half lambda. Okay. Any question? This is for destructive. For constructive interference, or bright in this case. So it should be cos squared equal what? And similar as above, yeah, the derivation where you will get this should be d sin theta and lambda. Okay. Is there any question for this case? Any question? No, okay. If not, let us continue. So this is the case. So we will get that for maximum, the bright fringes, yeah. So we will get this. Oh, I get this. You just replace m here by n, okay? Little n. Okay. and this is for the dark, yeah. So this the destructive interference. Okay, this is the minimum. Okay, this is for two slits. Okay. What about the picture? The picture. Okay, this is the intensity of this one. So this is basically the picture of the intensity of two slits. Okay, where we omit the width of the slit. Okay, only the distance between the slit, between the two slits. Okay, this is the picture. Any question? Any question? No, okay. Let us continue. Yeah, this is the derivation of this two-slit experiment. So this is the alternative derivation using the phasor diagram. Okay. So this is basically this two-slit. Okay, the wave from two slits. Okay, they have different phase phi here. Okay, if we draw, this should be the first and the second. Yeah, you can also first or second. You can choose anything. Okay, so they have this E1 and E2 have different phase of phi. Okay, so from this triangle, you will get that this relation. Okay. Any question? Any question?
Not yet, sir.
Not yet. Okay. So this I0 is the maximum. I think zeroth order. Yeah. Zeroth order means that this n here, this m here, m equals 0. Okay. I0. So basically, this is this one. This the main bright fringe. Okay, this is the first. This is also the first. Okay, this is the second, and this is also the second. Something like that. So this is zero, the zero dark fringe, metaminema fringe. Okay, this is the one, the first, and this is the second. Okay. So this is the sample problem. For example, if we have, if we have 3 light waves, yeah, using phasor, for example, so we get E1 here, then the phase difference is 0, okay, and we have E2 here. E2, the phase difference is 60 degrees, okay. and then this E3 here is minus. It means that this minus in the fourth diagram, and fourth region, okay, fourth domain, okay. So this should be like this. So basically the resultant wave is E1 plus E2 plus E3, okay. If you calculate the amplitudes, okay, at t equals 0, you will get this one, okay. Oh, sorry, this is the horizontal component, and this is the vertical components, okay. So the resultant, it should be using this Pythagoras theorem, you will get this one, okay. And this beta here, which is the phase difference, the phase difference between this resultant and the first waves, okay, we get this one. Okay, so basically we will have this 3 wave, the resultant is like this. Is there any question for this sample problem? Hello?
Yes, sir, no questions.
No question, okay. So basically, because we only consider the oscillation part, okay, we could have this basically this simplify the solution, in particular for fixed t, yeah? not only for what is it? Yeah, for t fixed, yeah? Not only for t equals 0. I mean, the picture is the same for t equals 0 and t equal for any point of time. Okay. No question. No question. Okay. Okay, then my question is, I ask to you, if this is t equals 0, okay, this is t equals 0, why we still have the horizontal is E0 cos 0, while in the vertical components, like this. Muhammad Faza.
Hello, sir.
Yes.
Perhaps it's because it's all of them are at T0, sir, but I'm not sure.
Yes, sir. Salim.
Yes, Pak.
Yeah, your answer?
I'm still not quite sure, sir. I'm still thinking about the answer.
Okay. Nicholas.
Yes, sir.
Your answer?
Maybe the why is it t equals 0? Is that your question?
For t equals 0, okay, why we'll still have this E0 cos 0?
I'm not really sure because maybe it's the initial wave, so there's still an amplitude. I don't really know, sir.
Okay. Okay. This one we only consider the oscillation part, right? Okay. This is basically if let's stop here. So sorry. Let's say this is E0, right? And this is omega t, usually. Oops. What? And this is the omega t, this one. Okay? So in that picture, we just take, so this should we have a,
Sir,
yes?
I think you haven't shared your screen.
Okay, sorry. Okay, sorry. You can see that?
Yes.
Okay, yeah. So this horizontal, this should be E0 cos omega t. And this is vertical, it should be A0 sinus omega t. Okay? So basically, if we take this t equals 0, it's like this. So the picture from in the book, sorry, like this. This is at t equals 0. Okay, this one. Is that clear? Hello.
Oh, yes, sir. I'm starting to understand now.
Okay, yeah. Okay. So basically, in general, the picture is like I show you in the whiteboard. So this picture is only for t equals 0. Okay. Okay. Is there any question? Okay, no question. Okay, maybe we will continue on Friday. So we will talk about how to divide you into a group. Yeah.